Today, I'll be presenting my work on accurate compiler optimization, independent function identification. So while I'm currently working and affiliated with MIT, this work is unaffiliated with MIT, and it was done purely in my time at Purdue. And this is work in collaboration with Nathan Burrows and Matthias Baer. You may know the last one. Yeah.
So reverse engineering of binaries is required for many purposes: malware analysis and malware strain analysis, library versioning and automatic patch generation in applications, copyright violations, and whatnot. However, it's really difficult to perform, and manual analysis really doesn't scale, especially when you consider there's approximately 10 to the 5 number of new malware samples on a daily basis that security companies find. So we need some kind of automated analysis to identify binaries, in particularly functions within these binaries. But why is it hard? Well, first of all, you don't get any kind of debug information or type information from the binary. And the binary itself is highly dependent upon the compilation environment used to generate that binary. And when I say compilation environment, what I mean is the exact brand and version of compiler, the optimization used, those kind of things that influence the final final generation of the binary. And because of those highly dependent that high dependence on the exact compilation environment, the output binary, the output assembly, can vary widely from the same source code. For instance, strlen, which is possibly the simplest non-trivial function one can write, can change by up to 70% just by changing the compilation environment. And while it's true that similar binary code implies function similarity, the inverse is not true. Dissimilar code does not imply differences in function semantics. Current solutions can be broadly divided up into two groups: static and dynamic. Static binary identifiers just look at the binary itself without executing any code. For example, bindiff and ASM2vec both analyze the actual binary. Bindiff computes a control flow graph isomorphism to compare two functions, and ASM2vec uses a natural language processing techniques to identify similar functions. On the other hand, dynamic solutions can do all of the analysis that static analyzers can do. However, they execute some or all of the instructions presented in a binary. Blanket execution and IMFSIM are two examples of dynamic binary function identifiers. However, both static and dynamic solutions use the same underlying principle, as in they measure code properties and assume that similar code properties implies similar functionality. However, as we saw in the previous slide, these code properties are highly variable and are very fragile when you just change one particular part of the compilation environment. So instead, we formulated the IOVec Function Identification. It also is a semantic binary function identifier. It requires no source code, but instead of measuring code properties, it instead abstracts functions into sets of program state changes, and that those sets of program state changes provides a unique function fingerprint that is highly resistant to both compilation environment, purposeful obfuscation, and even architecture changes. The reason why the the program state changes are resilient to all of these broad changes in compilation environment are because the compiler itself often will guarantee the semantics of the source-based code and then apply optimizations and changes to this code as needed while still maintaining the actual semantics within the binary, within the source code itself. IOVFI relies upon these units that we call input-output vectors, or IOVECs, that stores some initial program state and the expected program state that a particular function we should see after a particular function executes. A function accepts an IOVec if it executes to completion, starting with the initial state encoded in the IOVec, and the resulting program state matches what we'd expect also contained within the IOVec. And this set of accepted IOVECs is the unique function signature. So for instance, take this very simple function here that takes in two integer arguments and a pointer. This function divides the first argument by the second argument and then stores that result in the location pointed at by the third argument. And finally, this function returns 0. An IOVec would then set the first argument to any integer, and then the second argument to any integer except for 0. And the third argument can be any valid memory address. And the memory address located at that pointer can contain any value. And then the expected program state after this function executes has the return value be 0, no system calls were made, and the memory located at the third argument contains the value of A divided by C. Any single concrete instance of this IOVec that satisfies both this input and output state is a valid IOVec for this particular function. And the full set of IOVECs will uniquely identify this particular function from all the other functions within a binary. In order for IOVec to work, it first needs to go through a training phase. This training phase uses a guided mutational fuzzer to discover IOVec sets for every function in a binary. And then every generated IOVec is then given to every other function in order to establish the ground truth of whether or not a particular IOVec is accepted by all functions. Once we have this information, our system then generates a searchable binary tree with IOVECs as the interior nodes and known functions and unknown functions contained at the leaves. And then function identification is merely a traversal of this binary tree, where an unknown function is presented with a particular IOVec, and the path through the binary tree is determined through whether or not that particular function accepts or rejects the presented IOVec. So for this example here, we have a generated binary tree from some theoretical inputs and function sets. We can encode unknown functionality, which is also helpful for reverse engineering, so that an analyst can focus their attention more on the unknown functions in a new binary and let IOVFI classify the known functionalities. When we are presented with an unknown function, we start by giving that unknown function the first IOVec at the root of the tree, and then progress through the binary tree, taking the right path if the IOVec is accepted, and the left path if it's rejected. So in this case, we have some unknown function that accepts the root IOVec and then accepts the path to the right that IOVec, and then finally this unknown function arrives at a leaf, and we can say that the unknown function is this particular function encoded at that leaf through this path. However, if we're presented with a unknown function that encodes functionality that we haven't seen, then some IOVecs will be rejected, and a different path through the binary tree will be taken. And in this case, some unknown function accepts the root IOVec. However, it rejects all subsequent IOVecs, and so we arrive at an unknown function node in our binary tree. The particular function in question could then be a target of manual analysis or further automated analysis as needed. In order to evaluate the effectiveness of IOVFI, we compiled core utils using Clang and GCC at 4 different levels of optimization. We then selected the 3 medium-sized binaries in core utils as determined by the default compilation environment, and then used those trees to identify functions in the 5 largest and smallest binaries in core utils. And then we present our results as an F-score, which is the harmonic mean of precision and recall. The reason why we chose F-score is because when we want to reverse engineer a binary, we want to have both high precision and high recall, and we don't want to sacrifice one for the other. So when we compare against bindiff6, we always improve over the F-score that bindiff achieves. However, when the compilation environments are the same as in the bolded records, our improvement gains are fairly modest, about 22 to 24% over bindiff6. However, as the compilation environments diverge from what the training set contained, we get widely improved results over what bindiff6 can achieve. And we generally see a trend of an increasing accuracy gap from bindiff6 as the compilation environments change. And generally across the board, we get fairly high, consistently high F-scores despite widely changing compilation environments. We also compared our work with ASM2vec, and when the compilation environments match, again in the bolded records, we actually perform worse than ASM2vec. However, again, as the compilation environments change, we remain highly accurate, while ASM2vec F-scores drop down dramatically. IOVFI also scales to large binaries, as seen here, where we generally achieve, again, high F-scores despite changing compilation environments, even in binaries of much larger size. And as some extra results that we weren't able to fit in the paper due to size constraints, we also did an experiment on cross-architecture accuracy. So when since IOVFI is able to capture source-level semantics as expressed by the source code and not code measurements, we ought to be able to take IOVecs that were generated for one architecture and be able to use them in a different architecture, because the source level semantics remain the same cross architecture. So that's what we did. And we created a minor shim layer to translate between x86 IOVecs or IOVecs generated by x86 binaries and use those unmodified IOVecs to identify functions in ARM64 binaries. And these results are the results that we got when we tried to identify those functions in the ARM architecture. So, in conclusion, I've presented IOVec Function Identification, which semantically identifies functions in binaries. Instead of using fragile code measurements, we instead abstract functions into program state transformations and use those program state transformations as the unique function identifiers. Because the compiler largely guarantees semantic functions as expressed by the source code, it's resilient to broad changes in compilation environments and architecture, which I should mention is a first-in-class feature for binary semantic identifiers. We've open sourced our prototype at the listed URL, and I'll be happy to take any further questions.
I'm curious, I know a lot of works on binary semantic similarity checking are looking at the kind of structural similarity, and there's a lot of machine learning models for this. Have you compared any of those in some of your experimental works on this?
Well, IOVec is a machine learning model, and the issue that we saw with machine learning based systems is that it's very hard to fully capture the available semantic expression space. There's basically too many ways to do the same thing in code, and it's very hard to capture all of those. And in particular, if you have a small set of binaries that like malware and stuff like that, it's very hard to identify the functions in these small sets of binaries. So we think something a little, I don't want to say more principled, but something that doesn't rely too much on big data sets or stuff like that is the way to go in this area.
Cool. Thank you so much.
I have one more question. So, how confident are you with this claim that IOVFI doesn't change with the compilation environments, right? Because there are many recent studies now that say O3, even O4, they don't include all the compiler optimizations. They include maybe 45% of all the compiler optimizations. So, how confident are you in making the third claim?
So our evaluation took a look at all of the different optimization levels from O0 to O3, and we achieved similar F-score accuracy, regardless of the optimization used in training or in the evaluation set. So I'm fairly confident that any kind modes of obfuscation. One where instructions are replaced with semantically equivalent ones, or another obfuscation is the adding of bogus control flow, and there's a third mode, control flow flattening. So it replaces loops and stuff with a whole bunch of branches and stuff like that in an effort to evade analysis. Well, because we don't measure code properties, all of that stuff is meaningless because the LLVM obfuscator still preserves the source-based semantics. So we are able to execute purposefully obfuscated binaries with the specific input state that we set, and the output state is guaranteed by the compiler. So the output state that we measure, however you get there, is what we measure.